Hello. For today's Math Chalk Talk, I'd like to talk about a game I'm going to call Infinity Questions. First, I'd like to talk about the purpose of these talks and why we've been talking about mathematical topics, including measure theory-based probability. Well, when teaching even very standard material involving probability, you get brilliant participants and students that ask questions that you really don't have time for in class. Now, there are several interpretations of probability we use in our practical work. Frequentism, which says most all probabilities are mere rates of reoccurrences. Bayesian probabilities, which is more subjective, that they're subject to certain calculations and also have prior beliefs and posterior beliefs. And the core between all models of probability is exactly what calculations are you allowed to make. So mathematics, again, comes from a position of fear, that even the calculations we say we can make cause enough trouble. We need a rule set saying there's even more calculations we don't trust. So the core of measure theoretic probability is what sets are you allowed to ask for the measure of, and what calculations are you allowed to make. The list is actually quite small. We can do a few things, like if we have two sets of events that are disjoint, the probability of one or the other happening is the sum of the probabilities, assuming everything is measurable. If we have two events that are independent of each other, that knowledge of one doesn't change the probability of the other, then the probability of both of them happening is then the product of the probabilities. So there's certain calculations treating probabilities as mere numbers that make sense if we obey the laws of probability. Now, probabilities that we tend to use in data science tend to be discrete probabilities modeling things like cards and dice. However, we can easily get continuous probabilities or real numbered probabilities by asking, like, what's the odds of if I spin this chalk and place it that it crosses this line? This is a Buffon's needle problem. So we rapidly get into what calculations over probabilities are correct over the real numbers. And it sounds a lot like calculus or measure theory, which it is, though it's a little more subtle than either of those fields are. Now, back to why are we lecturing about these abstract mathematical topics? Well, it's student questions. That they often say, you're teaching us all these rules, can you tell us what happens if we don't have these rules? And the answer is, with some preparation, we can show you what happens if we don't have these rules. So I'm going to introduce a game called Infinity Questions. Obviously, it's a generalization of 20 questions. We're going to ask arbitrary number of questions and see what happens. And we're going to do this in terms of measure theoretic probability. The first thing is I'd like to return to the nature of infinite. We see in mathematics often things like infinite sums. Now, in standard mathematics, we never really deal with an sum with an infinite number of terms. We say that this is very well approximated by finite sums and by a continuity argument. If this sum has a value, then it must be the following value. So this is equal to the limit I goes to infinity. Sorry, n goes to infinity of 1 over 2 to the I. And we appeal to a notion of continuity to say, even though we can't ourselves sum up an infinite number of terms, we can work out what that value must be if this is a continuous function of this index n. And that is how we deal with the infinite, and that's how we're going to deal with infinity questions. We're never going to ask an infinite number of questions. We're going to ask an arbitrary large number of questions. Now, our game will be played on the unit interval. So that is all the numbers in the range 0 to 1. Probably we'll make this a closed end and this an open end. 1's probably not in the set, doesn't matter, but just to be precise. Now, the other player in the game has picked a number, x, say a third. In the game, we don't know the number. We're just making it concrete to make the game easier to explain. Then, the type of question we're allowed to ask is simply, is x in this interval? So A is less than or equal to B. So we're allowed to ask any question, is x in the interval a, b, and we'll go ahead and allow the left side to be inclusive or exclusive and the right side to be inclusive or exclusive. So any question is the form of this. For instance, we could ask, is x in the interval 0 to a half? And the answer is yes. So from a computer science point of view, this should lead us to the idea of bisection search. If x is a value on the interval, and our game is to find it by asking if it's in various sets, we want to find the actual value of x, well, the computer science solution would be to basically recurse. If we know it's in this interval, then maybe our next question would be 0 to 1/4. And that would be no. So now we know it's in this smaller interval. And we can continue to reason by what is called bisection search, that we always have an interval we know x, we suspect x is in by the questions as it's been answered, and we cut that interval in half and eliminate half the points. Now, this can run forever, which is why it's infinity questions. However, these abstract axioms of measure theoretic probability include an important axiom which might seem very abstract, but as I've said, it's discussed very well in this original book, much better than it's discussed in the later secondary materials. The idea is, if we have a sequence of sets, A1 contained in A2, contained in so on, and the limit, well, let's not say the limit, let's just say the intersection so assume each of the AI is measurable and their intersection is measurable. Could be the empty set, could be something bigger. If we have this, then make that an N again, my favorite mistake. This is what Kolmogorov's last axiom says, that if I can take finite intersections and compute the probability of these sets, like the intersection of the first n AI, and that limit exists, and the set B is measurable, then this limit must agree with this, that the measure of this limit is the measure of this destination set. So even though no finite intersection of these sets may exactly equal B, if the infinite one is, then this limit has to be approaching the measure of what the set's approaching. This is a continuity principle. So again, Kolmogorov isn't saying that he knows how to take infinite intersections and compute the measure of them. He's just saying if they behave in a continuous manner, he can infer what the value of this must be if there is one. So when this axiom is active, the game of infinity questions works. What happens is that for any point not equal to x, there's eventually some interval that y is not in. Eventually the interval around x becomes so small that y is outside of it. So any point that isn't the right answer, eventually the bisection search in a finite number of steps excludes that point. The continuity principle is saying that since each one of these intervals had measure 1 in this game, the intersection of all of them, if we continued forever, if we extended the game to infinity, which we cannot do, but if we could, then the measure of the intersection of all these intervals would also have measure 1. That set intersection of all intervals, as the intervals get half the width again and again and again nested, has to be a single point. It can be no bigger than a single point because, as we said, any point that's not the one that's answering the questions is excluded. So that is what we mean by we can play the game of infinity questions. We can't actually ask an infinite number of questions. all we're saying is the limit of asking a very large number of bisection questions converges to exactly the point that is answering the question, where basically the measure question is an interval is measure 1 if the item is in it, and measure 0 otherwise. Now, what happens if we don't have this axiom? If we don't have this axiom, the game of infinity questions can be made to fail. And that's the punchline. So how do we do that? Instead of saying AB, so original system PAB equals 1 if x is in AB, that's the original system. We make a new liar's system, which is defined as the measure of an interval AB equals 1 if exists C and the interval, open interval, C x contained in AB. Open interval means these are all the points that are strictly less than x and strictly greater than c. So x and c are not in this little interval. And c has to be less than x, strictly less than x. This is a non-trivial, non-empty open interval. So, and 0 otherwise. And this one is also 0 otherwise. So it says basically, this is my liar's left measure system, that an interval has measure 1 if there's a leftwards neighborhood of x inside this interval, and otherwise it's 0. This behaves exactly like a standard exposure distribution where every set has measure 0 or 1 depending on whether x is in or not for a different x. The idea is for any finite number of questions asked, it looks like we're bisecting searching to a point, even asking for arbitrary intervals. So if we ask a finite number of interval questions, then there's always an x prime less than x such that it looks like we were searching for that point. Now what x prime it is differs on what questions we ask and how many questions we ask. So the lie changes if we expose enough, but for any finite number of questions, there's an x prime that masquerades through them all. It's basically the average of x and all of the interval points that were left of it during the query game. That generates a point that behaves just like that had been the one we claim we're searching for. So this liar's search, it acts as if it's this one here with a different x, but it isn't, because it fails this limit. In particular, for every x in the liar's system, p x x, make that a closed interval, equals 0. Whereas in the real system, p 1/3 closed interval 1/3 equals 1. The point we're trying to guess is the unique singleton point or set that has measure 1. However, in the liar's system, all singletons have measure 0. So you can run this binary search, think you've got infinitely close, arbitrarily close to the answer, and it turns out there is no answer in that interval because this whole system was designed to never have an answer ever. And this is, again, a principle of continuity, that arbitrarily large, many questions problems should look like infinity questions problems. That's what it means to be continuous. Now, that's something we have to establish through axioms, and the axioms would forbid this measure. This measure violates this axiom. So this axiom prevents this measure from being what we're exposed with. Which means, to summarize, when you have the Kolmogorov limit of intersections equals probability of the limiting set, then we get, for this really cool measure, I'm going to call the exposure measure, where every set, as we've said before, has probability 0 or 1, depending on whether our hidden point x is in it or not. That measure is only derived from having picked a point. There's no other way to set up this false system, or any false system, where we didn't actually pick a single point, where we've hidden our mass in some sort of weird system. And that's the nature of my latest Measure Theoretic Probability Chalk talk. Again, a practicing data scientist would never use this because we don't really do data science over the real numbers. However, we don't stay very far away from it. Many probability experiments, such as if I throw this marker at the board, what's the chance of it crossing a particular line, have real number probabilities to our mind, and we rapidly run into calculations that we wonder, am I allowed to add these two probabilities? Am I allowed to take a limit here? Am I allowed to exchange limit and calculation? And that's what Measure Theoretic Probability says. It says, under these conditions, this calculation is guaranteed to not be the problem. You're allowed to make that calculation. And in most cases, it's replacing a very large finite system with a corresponding infinite one and knowing the answer. For instance, it is well known that this sum, 1 over powers of 2, starting at 1, this sums up to just 1. Now, that doesn't mean that we can take an infinite sum. It means we can take these arbitrarily large sums and prove that at some point they stop being any distance away from 1. Or for any distance away from 1, eventually there's sums that stay closer than that. And that's the same with probabilities. We can't run the infinity questions game to infinity, but if we can imagine running it to arbitrary long sequences, we can prove that it is only consistent with the answerer having chosen a single point to answer all the questions, if we have this axiom. If we don't, then this liar's system is possible. And that's the computer science way, or programming way of thinking of axioms. What algorithms work given these axioms? And the Kolmogorov continuity axiom for probabilities means bisection search works in that it's limiting down to a single point. And that's what I wanted to say. This may seem a little strange, but what I'm trying to do is give some of the joy of thinking about probabilities without having taken the whole semester course in Measure Theoretic Probability. So this is sort of a conclusion. We may not have given enough to support all this conclusion, but a Measure Theoretic class would. But this is hopefully a little capture of the joy when you run into this sort of fact. Thank you very much for your time.